Okay, we should be live. Can you double check?
Yep, I'll check. Yep, we're live.
All right. Hello, everyone. Welcome to Corecast. I am your host, Tim.
And this is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. If you haven't already, do join our Discord channel. And if you're watching this on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode, and we'll get to it. And then also we're planning shorts, making of shorts. So if you have any ideas of for video clips that you want to see us talk about, please do let us know. All right, so now with those logistical things, let's get to it, Tim. So last time, Tim, we talked about an interesting Millennium Prize problem, and for those who don't know what Millennium Prize is, this prestigious award, like prestigious set of problems in mathematics, get $1 million for solving them, like Riemann hypothesis, P versus NP, so on and so forth. And we talked about the one that's most tied to physics, even though it's very mathematical in nature, which is Yang-Mills. We'll cover that very briefly. And the main crux of it, as you were talking about, Tim, is that you can generate mass like just by force. And we'll definitely dig into that in this episode. And I wanted to know, like, yeah, so I guess like, what does it mean to like, how can you have mass without matter in the theory? Like, what does that even mean?
Yeah, and so I think that this basically gets at the crux of the Millennium Prize problem that we just described last time. Basically, the prize will be awarded for a mathematically rigorous formulation on how a very specific theory, Yang-Mills theory, is able to generate mass from pure force. And so last time we kind of covered some of the basic physics behind it. The basic intuition is that if you look at some of the more typical forces that we're familiar with, let's say electromagnetism and gravity, there is no mass gap. And for the audience who are not familiar, what does it mean when a force doesn't have a mass gap? It just means the force feels intuitive. Like for example, look at the sun. Well, I don't recommend that, but like when you feel the warmth of the sun, the light from the sun is coming onto your skin. The reason why the particles of light, photons, is able to be generated in such copious numbers, and also it's able to travel very far and at the speed of light to you, so that you feel the force of the sun, is because a photon has no mass. And in a very similar way, the reason we feel gravity, we can feel the gravitational pull of the Earth, and the Earth orbits around the sun because it feels the gravitational pull of the sun, is also because the gravitational force carrier, graviton, does not have a mass. So gravity does not have a mass gap. So these familiar forces does not have a mass gap. But yet, it seems like back in the 1930s, 40s, when physicists tried to generalize these forces into what we call the Yang-Mills theory, which is actually mathematically it's a very natural generalization of electromagnetism. They find out that lo and behold, the forces are different. They create what we know as a mass gap. It kind of removes this feeling of what a force is. And so that's kind of the conundrum. And we want, mathematicians and physicists alike, they want to find out exactly why. And that's why there's a Millennium Prize to prove it.
I guess we've thrown the word mass gap several times. Could you dig more deeply into what that means? Make sure our audience is on the same page. What does it mean? And then what does it mean in the context of forces not having this mass gap?
Right, exactly. Yeah, yeah. For those who are unfamiliar, this is something that we take for granted, and that's like just look at everyday life. Just look at the table in front of us, or people that we're friends with, trees, the ground, right? The reason why these objects are so persistent, let's put it that way, is because in everyday life, mass is neither created or destroyed. Right? We walk outside,
Mm,
a tree is a tree. Maybe the leaves will fall and whatnot, but mass generally is conserved most of the time. Right? Einstein's theory says that if you have enough energy, you can create mass, of course, and vice versa. But generally, that doesn't happen. You don't go walking around seeing nuclear reaction happening. Oh, well, of course, caveat, the sun is a nuclear reactor, and the reason it shines is because mass is converted to energy, but let's not get into that, right?
mm,
But for most of our everyday life, the reason matter feels like matter is because matter has a mass, and more importantly, there's a mass gap. You can't just create matter out of thin air willy nilly because there's a mass gap preventing you from doing it. So, mass gap, you can sort of think of it as the differentiator between force and matter. Forces conventionally does not have a mass gap. Matter
mhm.
has a mass gap. So naively, back in 1940s, 50s, you wouldn't be wrong if you just assume that having a mass is a privilege afforded by matter, but not forces. That would be very reasonable.
Huh. So are you saying like, I'm just trying to think of a good example. If I were to, let's say move my hand really fast back and forth, it might generate photons very easily, for instance. But me moving my hand back and forth won't generate, let's say, I don't know. I'm trying to think of a neutral matter particle, like some, or maybe like electrons or something like that. For instance, is that analogy fair? Or
Yeah, that's basically it. It's like turning on a flashlight. You put some batteries in
Mhm,
it, you turn on a flashlight. Even your smartphone does it. Flashlight mode. Bam! You're generating photons, right? Photons are beaming out of it. But if you have a flashlight of, let's say, neutrons, well, that would be very hazardous, right? Like the only way for us to do that is like if you have some, I don't know, some uranium sources where fission is happening and neutrons are
mhm,
blasting out. And that would be very hazardous. And by the way,
mhm,
those are not creating neutrons, right? It's just neutrons that are flying off the material. So you're still not creating neutrons. But it's like
mm,
there is no flashlight for matter particles. Otherwise, you'd be blasting nuclear, reactions everywhere. Like will not be good, probably.
mhm. Yeah, I guess maybe we can talk about this later, but I want to ask in the context if you're like, say you have a really high energy flashlight, like insanely high, maybe more than the LHC, several orders of magnitude or something like that, then we've mentioned several times in the podcast, then it would be easier to create particles that just kind of pop in and out of existence, or
Right. Yeah. Yeah. Certainly. If you have an incredible amount of energy, enough to create like
Mhm,
galaxies and whatnot, popping
mhm,
a neutron out of it would be like nothing. Then when you have so much energy, yeah, sure, the difference
mhm.
between the mass gap effectively becomes unimportant. But still, like
Mhm.
let's say if you have a thousand times the mass of a neutron, the
Yeah.
maximum number of neutron you get is 1,000. Right? Like you can't overcome that. But guess what? The maximum number of photons you can generate is almost infinite. I'm just
Mm,
waving my hands. I'm generating photons. Like you cannot detect it. But that's what happens when you don't have a mass gap. I can just willy nilly create force carriers left and right.
mhm. So you're saying that mass gap ge- is like a proxy for how difficult it is to create said particle, or is that is that a fair statement? Or
Yes, yes. Mass cap should be thought of as a barrier to access whatever you're trying to access. And for the case of matter, it's the barrier to creating more matter, you know. Um, and
mm,
we generally don't think of mass gap as being a thing associated with a force because you just feel the force, right? Like I don't
mhm.
know what's a good analogy. A force is just something that you feel. If there's a gap, it's kind of like what you just can't feel the force. Like that would be kind of odd. But it turns out that that's what's going on.
Yeah, yeah, yeah. I guess like why is this a big deal? Like it's just okay, like matter has a mass gap, forces, at least the ones we've discussed don't have a mass gap. Like what yeah, just why is this even worth even discussing? It just seems apparent. Is it not as obvious or
Yeah, well, what the interesting thing is, it seems like even though it seems like forces don't generate mass gap, but that turns out to be false, right? When we generalize
Mhm.
electromagnetism to Yang-Mills theory, it turns out that Yang-Mills theory just generates a mass gap. At least
Mm,
when we run simulations and experiment, and
mhm,
it's just really weird because Yang-Mills theory is not that different from electromagnetism, as we
mhm,
explained before. It's a very natural extension of a symmetry. When you add self-interaction in a self-consistent way, and you also let it play well with symmetry, and check out our previous episode, you arrive at Yang-Mills theory. And for some reason, the moment you add in these self-interactions, the force kind of took on a totally different flavor. It just totally changes the way forces are. And that's just is really strange. Like it's almost like a phase transition.
mm.
It becomes something completely different. Um, so that's why it's a mystery.
I see, I see. So are you saying like so we've discussed electromagnetism that it's really easy to create photons. Like me just waving my hand will simply cause photons. I mean, may not be detectable by our eyes, might be too long of a wavelength or too low of a frequency to be in the visible spectrum, but there are photons created nonetheless. Whereas Yang Mills, which is a generalization of electromagnetism to the other forces, we'll talk about that in a moment. You're saying those have a mass gap, so it's not like it's kind of like if I were to like wave my hand, I just can't create those force carriers that have a mass gap. Is that right? Or
Yeah. So the mass gap has multiple consequences. Like the most
Mhm,
basic version is just that in order for you to access that force, you need to have enough
mhm,
energy to create those force carriers, and those force carriers
mhm,
have masses. It also means that mathematically, I mean, this is a little more technical now. It means that a lot of the properties of the forces are exponentially suppressed. So you don't see them at large distances. And this is what
mhm,
happens for the strong force and the weak force. Although the reason why they have mass gap is a little different. We can get into that.
mhm,
You don't experience strong nuclear forces right now. Like my left hand, my right hand, they don't feel the nuclear interactions between them. Of course, that would be bad if they do, because if I clap my hand, then a nuclear reaction will happen. I'm sure the FBI wouldn't like that very much, right? But we don't see that happening, right? So the strong force turns
mhm,
out has a mass gap, and the same thing as the weak force. My hand don't just undergo radioactive decay. It doesn't happen. It's suppressed because of that mass gap. So these are real physical consequences. So unlike some of the mathematical problems, this is real life physics, really. Like it's related to
mhm.
real life physics.
Makes sense. Makes sense. So, definitely as a primer, we're going to talk about this in the context of the strong force, which I assume this Millennium Prize problem is related to. So, Tim,
Mm-hmm.
I'm just going to ask you point blank, how do I win $1 million? I want some money. What do I do?
Well, we have to solve in the context of this Millennium Prize problem. You just got to find a proof. Um, I'm sure mathematicians have tried, but as a physicist, we don't exactly know what it takes to get the mathematics right. But we have some ideas about physics, and I would say the crux of the problem is um, how do you wrangle something like a mass out of a theory that doesn't have a mass? I know this sort of sounds a little bit ridiculous, but we can explain that a little bit. This property of the Yang-Mills theory is called dimensional transmutation, and what it does is kind of as crazy as it sounds. It really is a sort of transmutation. You just kind of grab it seems like the mass gap is just falls out of thin air. It's like turning
Hmm.
lead into gold. Like it really is bizarre.
Hmm. So, I mean, you're invoking some alchemist type of notions here that almost seems like magic. I guess maybe an analogy would be helpful of like why this idea isn't as crazy as it seems, as you're making it out to be.
Yeah, first we have to understand what the problem is.
Hmm.
Like from a computer, let's say from a programming angle, you know, the Yang-Mills theory, it's some sort of black box, and the
Hmm.
input of the theory, at least what people thought about, was just a number. Let's say you have the Yang-Mills theory with a interaction strength. You can input that as a number. The interaction string might be zero point 0.1 or zero point 0.01,
Hmm.
right? And in previous episodes we talked about the space of theories. You can think of there's a space of Yang-Mills theory, right? So
Hmm.
first you can pick uh, how much symmetry you have. This is a little abstract. You have to pick the amount of symmetry, some sort of geometry shape. You can pick like a sphere, for example, symmetry of a sphere or hypersphere. It's your choice that you can choose. And then there's a number called the coupling strength. It's just how large, how strong the interactions are. Is it zero point 0.1, zero point
Hmm.
0.01, 0.001, or is it 10 or 100, right? Anything you can choose. Um, but somehow, imagine you input that information into a computer, into this black box. Somehow it has to tell you what the mass gap is, right?
Hmm.
Now, if you dig a little deeper, like it doesn't, like the program doesn't even have any concept of mass. The numbers that you put in are just numbers. It doesn't even have a unit. So how
Hmm.
is it even possible to get a mass? Like, and should the mass be in kilograms? Should it be in like, I don't know, pounds, in grams? Like, what unit should it even be in? Like, the theory has no knowledge of that. So that's really mysterious. Like, it seems like even if you think of it as a black box, something is amiss. Right? That's why we call it transmutation. Like, it's still missing something.
Hmm. Yeah. So what you're saying is this theory doesn't have any notion of like units, even like kilogram, pounds, whatever. There's just a bunch of these numbers that you input in, and out pops this mass if you were to like put it in a computer. Is that what you're saying?
Yep, exactly, exactly. Basically,
Hmm.
there are these theories. Technically, they're just theories of numbers. But then
Hmm.
these have real world consequences, right? Like these are real world theories, or at least a simplified version of it. But we know that yeah, Yang-Mills theory has shared many similarities with the strong force. Um,
Hmm.
so that is the conundrum. So in order to to show this property, prove or disprove that there is a mass gap, we first have to understand where does the unit of mass come from, and how is it possible that it fall out of nowhere, or is something amiss?
Yeah, that is very strange. I guess like what is it about? I get is this limited to just computers? Like, what if you just try to do it by hand even?
Yeah, I think that the thing is, well, of course you can't do it by hand because the mathematics is complicated enough. It is very
Mm,
complex. If you look at but physics does give you some hint.
mm,
One way to think about these theories is to, in one of our older episode, is to Feynman's path integral. So somehow you need to sum over all possible paths or configurations and whatnot. Um, and I think from physics, the crux seems to be that the theory actually is not well defined yet. The theory
mm.
is just missing uh, that mass parameter or something like a mass parameter for it to be well defined. So it's almost, the theory itself is almost screaming at you, telling you that, hey, look, uh, I'm not well defined yet. Like you need something more. And I think when we discover that something more, the something like a mass parameter might show up.
Hmm. Huh. So what is this something more then?
Um, the truth is we don't know. I mean, an analogy probably when we talk about mass, it's a little hard for the audience to understand. But this is sort of a lesson in real life. Like everything requires context.
Hmm.
I think we thought about this. One good analogy is, let's say, the price of something. Let's say the price of a home. You know,
Hmm.
imagine I tell you I have a house, and then let's say the theory is to try to compute what the price of the house should be worth. How much should I
Hmm.
sell the house for? Right? And you say I have a house, and the house has, let's say, this many square feet. 2 bathrooms, 3 bedrooms, something like that. And you go to a realtors. You be like, well, I want to sell this house. Give me a price. And then they'll be like, hey, look, I don't have enough information to ascertain what the price is, because you don't tell me where the house is. This could be in the U.S. or some random country in the Middle East, right? Like those will be worth vastly different prices. Like maybe the houses on
Hmm.
Mars. Like how am I supposed to know how to value the homes? You know. So
Yeah.
in so how do I fix this problem? I mean, this is kind of like a pricing problem for the Yang-Mills theory. Like how do you price the mass of the particles in the theory? Basically, that's the quest, right? One
Hmm.
way to resolve it is to have a bit of a reference.
Hmm.
If I say my house is like my friend's house, let's say it's a little bit smaller, has 1 bathroom instead of 2 bathroom, and his house sells for, I don't know, $1 million. Then the realtor can work with me and then maybe come up with a price, because, like, hey, look, and also $1 million, let's say, right? Because the unit matters. Who knows? Maybe this is like Zimbabwe money, right? And that would that would be very different. So it's almost like the Yang Mills theory is screaming at you, like, be like, hey, I need some context. So we need some context. So maybe the context is what is needed to fully define the theory.
Mm. So, so what you're saying is like you need some reference point, much like in the housing example. And so, I guess when you're doing things with this theory, you require some notion of a reference point, and that reference point somehow relates to the mass gap itself.
Yeah, yeah. And in physics, dimensional transmutation is actually pretty clear.
Hmm.
It's basically telling you that, hey, imagine you try to write down Yang Mills theory, and you
Hmm.
say Yang Mills theory has the strength of this Yang Mills theory is 0.05. Let's say you say that,
Hmm.
and then let's say you try to do a computation. You will realize that you cannot do this computation unless you provide a reference scale, an energy scale. So So a proper way to define a theory will be like, hey, the strength is 0.05, but only at energy, let's say, some units. Let's say
Hmm.
at 10 GeV, right? These are particle physics unit. But what that means is if I shoot particles with roughly that energy and collide them, I will observe an interaction strength about 0.05. And that 0.05 will change depending on my energy scale. So in order for me to define the theory, I can't just provide a number. I need to provide something linked to some dimension. And in this case, it's
Hmm.
energy. And maybe through Einstein's equation, energy will convert to mass.
Huh. I mean, that seems to make sense, but can you explain further? I thought like mass is like more of a fixed quantity. Why is it energy dependent? Like the mass of an electron, like it's given in textbooks, it's written as a constant. It's not like, oh, at this energy value it's this, and at this energy value it's this. If I open like a Newtonian classical mechanics textbook, or even a quantum mechanics textbook, I don't see like a mass dependent on energy. So what can you explain that a bit more?
Yeah, and actually, it turns out that mass is just one of many quantities that are actually not constant. And
Hmm.
even though this dimensional transmutation seems bizarre, at the end of the day, it actually is ubiquitous, and that's the strange. That I guess is the stranger thing. Like for example, in the textbook, you says, "Oh, an electron has a so and so mass." It
Hmm.
means that in the limit, when you really hit it very gently as possible, you approximately get that mass. But it turns out
Hmm.
that if you decide to shoot the electron, or at least try to measure its mass, with a little bit more energy,
Hmm.
its mass does change. And
Hmm.
for electron, this change is very minute because electron doesn't have a lot of interactions. But it turns out for particles like the quarks that has strong interactions, or even the things that has mass gap in Yang mill, well, maybe these are not the best example, but anyway, masses in general can change depending on the amount of energy you probe it, just like the interaction strength of something. So nothing turns out to be. I don't think there's anything really that isn't energy dependent. I think energy dependence is the norm, actually.
I see. I see. I guess then my question would be like, I remember from learning relativity, there's a concept of a rest mass when a particle's at rest. And the mass does change depending on like which reference frame you're in. But if I'm in like the stationary reference frame of the particle, it has a constant mass. So in these experiments, you're talking about like gently like measuring it. What if I just gently measure it? Like I just restrict myself to gently measuring things, and it's constant from that respect. Um, I'm just trying to understand like what is the significance of energy like having to do with this? Like the forces that you mentioned involve you observe them at higher energies. Like you don't typically see the strong force in our at least not overtly in our everyday life. It's only when you probe like the inner structure of a proton and neutron do you actually see these things. So given if a proton is like at rest, just relaxing, and you gently measure its mass, why would this argument be pertinent to that per se?
Yeah, I would say when you do that, it's just a convention, right? Because when we measure something, you can never like quantum physics tells that you can never be so gentle that you don't impact it.
Hmm.
And there's always a little bit of ambiguity. And even though,
Hmm.
sure, you can define rest mass as some sort of theoretical limit, it is not a practical thing. Like sometimes to probe certain forces, you have to have certain amounts of energy to overcome certain mass gap, right? Let's say you want to create an electron positron pair,
Hmm.
then the energy of your beam has to exceed that. Otherwise, you can't do it. And let's say you're trying to create electrons and positron using a beam of proton, right? Guess what? Then the proton mass will come into the calculation. And that proton mass, let me assure you, it will not be the rest mass by that convention. And so,
Hmm.
certainly we can define masses by some conventions so that it's fixed, but it's very artificial, I think. I think the physical mass that another particle feels um, is probably the more realistic physical observable. And this goes
Hmm.
beyond Einstein's definition of rest mass, or whatever. It goes beyond that because, um,
Hmm.
and let's not get into the technical details because many of these relationships that you learn in high school physics, college physics, they are modified. And when energy
Hmm.
increases, and even the identity of a particle can be modified, as some of our previous episode has shown.
Hmm.
So in some sense, it's not just dimensional transmutation. It's basically everything transmutation. Like everything gets transmuted. That should be the norm. Yeah.
Yeah, that is interesting. I guess I would be. remiss if I didn't, in this discussion of mass, many people have heard from all these popular science articles like Higgs boson this, Higgs boson that, Higgs boson gives mass to everything. Where does that fit into all this? Like, why can't you just attribute this to Higgs and be done with it?
Yeah, the truth is, it most of all the masses that we observe do not comes from the Higgs field. I think that's a big misconception.
Hmm.
Um, I think you can say that many force fields are able to generate masses. Um, what is mass? Mass is the ability for a particle to slow down, and that's probably the proper definition. For things without mass, it travels at the speed of light. If you travel at the speed of light, by definition, you don't have a mass. Um,
Mm,
as long as you're able to slow down, you have acquired mass. And the more, I guess, slow down you get, the more mass that you get. The Higgs field is just one of many possible energy fields. I don't know how to call it. Quantum fields, really. That's the right word.
mm,
If you interact with the Higgs field, you get slowed down, you gain mass. And protons
mm,
certainly interact with the Higgs field. But if you look
mm,
at that interaction, it's very small because the
mm,
amount of interaction between the proton and Higgs field is the raw mass from the quarks, right?
mm,
And even though the raw mass is a little ambiguous, like we were mentioning, the mass and energy which you're measuring it, it's still very tiny, right? So if
mm,
you do that calculation, you realize that what slows down the proton is the self interaction between the strong forces. The quarks, imagine inside the proton, it's just flying, zooming by, close to the speed of light. But then, as they fly in one direction, they can get yanked really hard by the strong forces to go to another direction. So there's sort of this picture.
mm.
Um, there is take picture called the popcorn, the bag model, whatever. It's just kind of intuitive picture. I don't know how true that is, but it gives you intuition. It's just imagine like a giant bag of popcorn, and it's just like the corks are the raging, just popping in up. But this bag is pretty elastic, so they rage one direction, but then it got slingshot to another one, and that's because the strong electromagnetic field. It's the strong it's this the strong force equivalent of electromagnetism, right, inside this bag, and that
Mm.
slows down the quarks and gluons themselves, and that's what really gives proton the mass. And this is like this interaction itself, we believe,
Mm.
is what generates the mass gap for Yang-Mills theory. It's just this kind of like a bounciness, slingshot-ish behavior of the strong electromagnetic field.
Oh, okay. So what you're saying is there's two mechanisms. I mean, maybe there are more, but based on this conversation, there's at least two mechanisms. One, the Higgs mechanism, which gives matter particles such as quarks, electrons, and other things their mass. But the case for a proton, you have, on average, it has three quarks in it, and the physics in there is very complicated. But those three quarks, if you sum up their mass, as we were mentioning in the previous episode, it's like far lower, like just like, just very little compared to the actual mass of the proton. And most of the mass of the proton comes from the strong force carriers, gluons, self-interacting with themselves and other gluons, such that like, that gives rise to mass. And mass can be viewed as like this slowing down that if things have zero mass, they move at the speed of light. But this sort of interaction that gluons have amongst themselves really slows down the proton. Is that a fair thing to say?
Right. Yeah, that's what we believe a physical picture. And just some corrections.
Hmm.
Protons have a lot more quarks than three. What we refer to as three quarks is what we call the valence quark. If you take if every quark has plus one, every anti-quark has
Hmm.
minus one, and you sum them up in this super weird calculus of
Hmm.
summing up quarks, you get
Hmm.
a net of three. Right, that's what you get. Um, and also,
It,
and
real quick, is it incorrect to say there are three on average, or is that like what you're referring to is the valence more than the number of quarks?
yeah, I think on average it's a bit false because On
Mhm.
average, I think an anti-quark still would count like as a positive quark, but I don't know. Some people disagree, right? If somehow average means negative, but I mean, an anti-quark doesn't have negative mass. I mean, but
That's
who
fair. That's
knows?
fair.
Yeah,
Okay. I guess maybe I use the terminology differently, but yeah, I agree with what you're saying. Yeah. 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 Thank you for the
yeah.
correction.
And I also want to add that probably we can argue that there's three known, well, known or slash semi-known mechanism for generating mass. Of
Okay.
course, there's a Higgs mechanism. There's a strong force for protons, and
Mhm.
probably dark matter exists, and dark matter probably requires a new mechanism for generating its own mass. But then that's a little more speculative. So there are probably a lot more mechanisms for generating mass. Um, but Yang-Mills and the Higgs mechanism would be the two main possibilities.
Gotcha. Gotcha. That makes sense. That makes sense. Um, so that's an interesting place to put the Higgs mechanism and this strong force mechanism. I guess where does this leave us? Like, do you know where people are in the in solving this Millennium Prize problem? What like yeah, what do people typically do?
Yeah, I would say that the physics intuition is there, basically. The mathematics is incomplete. We just don't know how to formalize it. And chances are something like dimensional transmutation need to be included. The theory, in order to define it properly, needs to have some reference of energy in order for that to be defined. Um, I mean, I personally, I don't know the mathematical difficulties. It's difficult. Like, you know, in some sense, like physicists, physicists don't exactly care too much. Like, we're happy with it. We have the intuitions. There are no proofs, but we roughly know maybe where we need to go. Um, Maybe the physics is very wrong. I mean, that could be true, but
Mhm.
I guess it's good enough for physics. But of course, it would be nice to see the mathematics confirming the physics intuitions, or maybe completely denying it. Maybe like all that physics intuitions are just misdirections. I don't know. Maybe there's something else that sort of give you that physics. I don't know,
Mhm.
but that's
Mhm.
probably where we're at. I imagine. I think that the problem is that this problem is just so different in flavor compared to other mathematical problems because
Mhm.
it's not even well defined yet. The question, in some sense. So, like, how do you even get started? Well, you need to build a paradigm to even begin the discussion, basically.
Mm. So are you saying okay, so let's say somebody okay, I guess maybe this is a bit more in the speculative territory. From in your opinion, if somebody were to solve the mass gap problem completely, it's well defined, well formulated, and I'm just looking at the output of how they do it, not just like how they do it, but would it be such that like given this current paradigm of dimensional transmutation, that if I pick a certain energy scale, then I'll be able to predict the mass gap that comes out? Is it just looking at like what is the relationship between mass gap and energy? In other words, saying that oh, mass gap is a function of energy. What does that function of energy look like?
I think it has to go deeper than that.
Okay.
I think the crux is really building the machinery
Hmm.
to define this physical theory. I mean, this is a little bit of philosophy, right? Like we
Hmm.
believe that physics ultimately is logical and is mathematical. So there
Hmm.
must be a mathematical structure supporting it.
Hmm.
And we don't know what that mathematical structure is, but it must exist because like real life is here. Of course, we didn't describe how the strong force isn't exactly like Yang-Mills, but it
Hmm.
contains Yang-Mills theory, right? So
Hmm.
at least the physicist intuition inside us tells us that hey, look, there's gotta be a beautiful mathematical object. So I think it's more
Hmm.
than just showing some relationship, blah blah blah. I think the crux is the proof. Proof requires a rigorous logical framework. And I imagine if the Millennium Prize problem gets solved, just having a proof, I don't think it's that valuable, right? Of course, it'll be great. It satisfies some curiosity. But
Mm.
what we will get is a more rigorous framework that we can define a theory beyond. We also described this in previous episode beyond, say, perturbation theory. We can
Mm.
just define this theory as it is, as its own object, without having this crazy extrapolation procedure. And maybe,
Mm.
and the hope is that it will help us just increase our understanding of fundamental physics, because Yang-Mills theory at the end of the day is just one example of a theory in particle physics, right? Particle
Mm.
physics is a lot richer than just Yang-Mills theory. We have the Higgs mechanism, we have gravity, and we have,
Mm.
if you believe in string theory, we also have things that are string theory like. They all have something like dimensional transmutation. Um, if we're able to rigorously define what it is, maybe we'll finally understand the inner workings of our universe. I think that's really the goal
Mm.
here.
Yeah, that makes sense. Maybe we can like it's probably the last thing I want to mention before we close out this episode. Um, is that like maybe you can touch upon very briefly if you're doing this computationally, where the notion of an energy scale comes into the computations, like how those are intimately connected with each other.
Yeah. So people have attempted to bypass this dimensional transmutation to just brute force it, let's say, on a computer, right? Like we
Mm.
have so much computer resource. Why not just brute force it? Who cares? It's almost like if you like the analogy of the home prices, just take every atom in the home and force a price out of it. You can try to do that. But what people realize is if you try to put the computer in a simulation, you don't have infinite computing resources. You need to
Hmm.
put physics on a grid, right? And it
Mm.
turns out that the mass gap that you get out of your theory depends on the grid that you put the simulation on. And that's not
Mm.
what you expected, right? Like if I were to run a simulation, I expect, hey, if my grid size changes, hopefully my answer doesn't change. But that's not the case. Your answer does change. So it's a hint that is telling you that you can't even brute force a calculation without a reference to some sort of size, a grid
Mm.
size in this case. And a grid size,
Mm.
you can convert a grid size into energy, because in quantum physics, we mentioned many times ago, size is like 1 over the energy. It's inversely correlated. So you can convert a
Mm.
size into energy, and then from Einstein's equation, energy to mass. So
Mm.
it seems like it is inevitable, this dimensional transmutation. You can hide, you can dodge, but you need it at the end. So you can't get away with it. So and it just seems like it's there, right? It's there.
Yeah, that's a fair point. But one other question out of my own curiosity is does the answer also change on a computer depending on how you represent the grid? Like most people when they think of a grid think of this three-dimensional cubic lattice, but what if it was like a different kind of lattice structure, even if the lengths were, equivalent to each other?
Yes,
I don't
it
know if you know
does
the
change.
answer to that.
It
Okay.
does change. It does change. But the key point is, some if you choose a grid that is kind of nonsensical, like some
Mm.
if let's say you choose a random grid, um,
Mm.
you might get a nonsensical answer that is inconsistent, because your theory has
Mm.
certain symmetries, and your grid better respect that. If it does not
Mm.
respect that symmetry, you've messed up your calculation. You've calculated the wrong thing. So, and if you respect that symmetry, the answer you get should not be too sensitive to the grid choices, but it will
mm,
be sensitive to the size of the grid choices. Yeah, but
mm.
this is very subtle
Mm.
details. It's not obvious.
Actually, okay, last question, I promise. So you mentioned respecting symmetries, but by discretizing, you've already broken like a whole bunch of symmetries because I don't know, the analogy I think of is, these particle physics theories, if they were, I know it's way more complicated, but if you were to represent them as a circle, you could like rotate them a continuous amount of degrees and the theory would be unchanged. Yet, if you instead change that circle into a bunch of like miniature grid points, then you have to like rotate it by like a discrete angle. So you've already broken symmetries. So how can you expect your symmetries to like be respected?
I mean, that's one of the problem. Actually, that's one of the problem with lattice calculations. It's
Hmm.
you don't necessarily respect all of your symmetries,
Mm,
and a lot of times it means that there's a lot of fine tuning.
hmm.
And I'll echo back to some of the episode, right? This is the difference between real symmetries and fake symmetries. Real symmetries does not require fine tuning. Like space time is
Hmm.
exactly the same, front, back, left, right, and if my arrows a little bit to the wrong direction, it's still okay.
Hmm.
Like you said, for the grid, that is not true. But
Hmm.
if you know what you're doing, you carefully fine tune it and you cancel out the spurious stuff that you computed, you could get sensible answers. But I'm not going to pretend to be an expert here, but like, uh, it is very, very tricky. And these are like
Hmm.
supercomputer calculations, you know,
Hmm.
who requires many, many physicists interpreting the answers and trying to understand them. So yeah, it is not straightforward. Let's put it that way.
Got it. Got it. That makes sense. Um, yeah. So I mean we're almost at time. So I wanted to give you a chance to leave the audience any words of wisdom that mass gaps and Yang mills and dimensional transmutations have taught you.
Yeah, I would say at face value, if you just Google Millennium Prize problem, Yang Mills mass gap, it just looks like, oh, who cares? Like it seems like it has nothing to do with real life. It's so esoteric, some abstract physics stuff. What gives? But I would argue that out of all the Millennium Prize problems, this is probably the most important for real life. And this might not be obvious because look, Yang Mills theory is almost one of the simplest theory because it's the strong force strip away with everything else basically. It's one of the
Mhm.
simplest theory that has a lot of non-simple interactions, and we
Mhm.
know what the physics is like. And we're just the Clay Institute is just asking scientists to put it on mathematical firm ground. And indeed, if particle physics is ever to have a fully rigorous mathematical ground, Yang-Mills theory should be one of the first one to have it. So so
Mhm.
they chose Yang-Mills theory as a starting point for good reason. Like not because it's some esoteric weird stuff. No, it's because it's sort of like a weakness in particle physics. That's the one thing one should go out and attack. And and that's what makes it so significant actually. Because look, whether you like it or not, everything that you see that you love, we live on this earth, ultimately is governed by particle physics.
Mhm.
Ultimately, there's logic in it that sort of like Gang's theory is governing what it's doing, and yet we don't know how to logically consistently define it. And this is really is just the beginning of the journey to get it in. Maybe we won't see it a solution in a lifetime, but look, many thousands of years from now, maybe we'll look back and be like, hey, look, that was obviously important, right? Um, so I just want to highlight that importance, and this is a difficult problem and an important problem to solve.
Yeah, that's definitely very encouraging. If you and I live 1,000 years, I hope it happens.
Yeah, just
Um,
personally, I know that there's a lot of YouTube video that asks, which Millennium Prize problem you would like to see solved. Many people say Riemann hypothesis. Not for
uh,
me, not for me. I want to see Yang Mill. I want to see Yang Mill's mass gap theory get solved. Give some logic to
and
physics, okay?
yeah, it would be the I guess like in your words, like one of the first steps in putting particle physics on firm mathematical grounds.
Yep, yep. Like forget Riemann's hypothesis. Yang Mill's mass gap,
I
problem.
I
Let's
have
solve it.
I have to say I'm more of a fan of Riemann hypothesis. But maybe I feel the same about P versus NP as you do about Riemann hypothesis. Yeah. Also, I want to thank one of our audience members for their idea for a short. We'll definitely discuss it and try to put one out in due time. But yeah, on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah, see you all next week. Bye bye.
Bye.